AP Calculus BC, Unit 8, Day 7, Office Hours. These are the answers. If you haven't checked them yet, pause the video and I will move the page. Okay, so you've checked those. 2, 4, 5. Okay. 6, 7, 8. And 9 and 10. Okay. So let's try these out. This kind of follows along the way that we talked about them in the lesson. So first one, error in a geometric series. Find the exact value of the error in the given truncated geometric series. So it's a geometric series. It's truncated. We're going to cut it off. First 3 non-zero terms would be these. Everything else afterwards is going to be your error. So, the error itself starts at 1 over 16. The R value here is 1/2, 1/2. It's going to be 1 over 32, 1 over 64. It is its own geometric series, the same geometric series, but starting at 1/16. So the sum of this series is a over 1 minus r, and the a value is 1 over 16, and the r value is 1/2. So we get 1 over 16 over 1/2. 1 over 16 times 2 over 1 equals 1/8 is the exact error. Number 2 is truncated the first 4 non-zero terms. What we could do is start to write it out. It starts at n equals 2, so be careful. The first term is actually 4/9. And then when it gets raised to a third power, you have a negative, so it's going to be minus 6 8/27 plus 6 16/81 minus 6 32 over 243 plus 6. Now it says first 4 non-zero terms, so that would be those terms right there. So it's going to be the series that follows this. So we need to find the next term. That'll be our first term. So that'll be 64 over 3 times 243 is 729. And then it keeps going. But our error is going to be equal to the sum of this series, a over 1 minus r. A is 64 over 729. 1 minus the r value is negative 2/3. So you have 6 over 60, 6 times 64 over 729 over 5/3. I'm trying to wait to simplify, multiply this all out until I can reduce it, hopefully as much as possible. I can take a 2 out of that, it'd be 2/3. That was sort of helpful. Take another 3 out of this and a 3 out of this, that would be 81. And I think that's how we can do it. So 128 over 405 is the exact error of the truncated geometric series. Usually it's not going to be that easy. Here's a couple, like one we did in our notes. Use a calculator to find 3 significant figure value for the error in this truncated power series. So this is the function. It's centered at 0. It's a Maclaurin series. And we're using it to estimate 0.5. There's a decimal there. The first 4 non-zero terms. So the sine series is the odd terms x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. So first 4 non-zero terms, so we're just going to use those terms to estimate it. So we're going to go ahead and plug 0.5 in, and it's going to be approximately 0.5 minus 0.5 to the third over 3 factorial, which is 6, plus 0.5 to the fifth. 5 factorial would be 24 out of 120, minus 0.5 to the seventh over 7 factorial. 6 times this would be 720. So what's 7 times 720? 0, 14, carry the 1, 50, 40. Okay. We're going to use our calculator. I guess you could use your calculator to do the factorials also, but it might take longer for a lot of them if you just be quicker if you just do it in your head. So 0.5 minus 0.5 to the third divided by 6 plus 0.5 to the fifth divided by 120 minus 0.5 to the seventh divided by 50, 40. And the value we get is 0.4794255332. The actual value of sine. So the error is going to be the actual value of sine minus this estimate. So the actual value of sine 0.5 minus the previous answer. That's not what I want to do. The actual value of sine 0.5 minus the previous answer is 5.37007 times 10 to the negative 9th. Scientific notation. So 3 significant figures, 5.37. We should probably round up for error. That's sort of a stance I think we should take, because we don't want to underestimate the error. So I'm going to push for that. Okay. And that's not 3 decimal accuracy. That's like, I don't know, 9 decimal accuracy or something. But 3 significant figures. Okay. Inverse tangent. Do you have the inverse tangent power series memorized? Do you want to build it? I don't want to build it, but inverse tangent comes from 1 over 1 plus x squared, right? That's how you get inverse tangent. I'm just trying to go through the motions of like, well, is it a test? And I can't remember how to do it. So this series would be 1 minus x squared plus x to the fourth minus x to the sixth. So this is going to be x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7. We're using the first 3 non-zero terms to estimate it. And then we're going to plug in 1/2. So the error is going to be the actual value minus these first of 0.5 of these first value, the first 3 terms with 0.5 put in them. No factorials on those. Okay, so we could just do this all at once. Inverse tangent of 0.5 minus parentheses 0.5 minus 0.5 to the third divided by 3 plus 0.5 to the fifth divided by 5. And we get negative 9.3572433 times 10 to the negative fourth. So let's go with that. The error usually we think of as like the magnitude of the error, not if it's over or under. So I'm not going to put a negative on it. Let's say 9.36 times 10 to the negative fourth. All right. Number 5 says let f be a function whose Taylor series converges for all x and that the nth derivative is always less than 2, the absolute value of it, then determine the minimum value of n of the Taylor series for f of x necessary to approximate f3.3 with an error less than 0.001. So we're trying to actually decide how many terms to go with to get within a certain error. So the Lagrange error bound, which you might just try and see if you can write down from memory, it's the n plus 1 derivative at some c value, x minus a to the n plus 1 power over n plus 1 factorial. So our error is less than or equal to that. So for us, and c is some value between the center and the value of x. So that's it. That's the Lagrange error bound. Now the nice thing about this is it's pretty much looks like the next term in the Taylor series. Same pattern. So our error is less than or equal to, now we don't know what derivative we want to take, but the only information we have is that they're all less than 2. So we just put 2 in there. The value that we're plugging in is 3.3. The center is 3. And it's to some n plus 1 power that we don't know yet over n plus 1 factorial. So I'm plugging in what I know, and I want it to be less than 0.001. So I just start plugging in values in. You could do n equals 0, which would be usually one term, 0th order. We could even replace this with just 0.3. So 2 times 0.3 to the first power divided by 1 factorial. L.E.B equals 0.6, which is not less than 0.001. Do n equals 1. So it'd be 2 times 0.3 squared divided by 2 factorial, 0.09, which is still not less than 0.001. So we're just working our way towards it. So next one would be 2 times 0.3 to the third power divided by 3 factorial, which is 6. And you can tell that the error is getting smaller, right? As we add more terms, which makes sense. I think maybe the next term, we're getting really close to it. I bet this one's going to be the one that is finally less than that. So 2 times 0.3 to the fourth divided by 4 factorial should be 24. You get 6.75 times 10 to the negative fourth, which is, now that's just telling me how many decimal places to move it to the left. So it'd be 0.130, which is less than 0.001. It's the first one. So n equals 3. Where they ask us for n or how many terms, it says determine the value of n. So that's how we could do it. Okay. Next one's let f be a function whose fifth derivative, they're giving you the fifth derivative, and x equals 0.5 is in the interval of convergence of power series for this function, then the Taylor polynomial of degree 4 centered at x equals 0 will approximate f of 0.5 with with a Lagrange error bound of not more than. So we're trying to determine the Lagrange error bound this time. So again, you should be able to write this from memory. It's the n+1 derivative at some c value, x minus a to the n+1 power over n+1 factorial. So for us, we got to figure out what value to put here. That's sort of the most kind of unknown thing. So we're plugging 0.5 in, and our center is at 0. So we're looking for a c value between 0 and 0.5. So the cosine curve, I'm going to just draw the cosine curve. I need some kind of evidence. So the cosine curve, we can do full-blown extreme value theorem, but we're looking at 0. Now, usually the cosine curve goes to 2 pi, which is 6.3 or something. This is pi, which is 3.1. 0.5 is like, this is like 1.5. 0.5 is just like this chunk of the graph. 0 to 0.5 is just that tiny chunk of the graph. So we're looking for the biggest value of this function on that interval, 0 to 0.5. Well, it's clearly the amplitude, so that makes it easy. It's just going to be 72. Okay? I mean, this picture for me is good enough as minimum lazy approach. Now we're plugging 0.5 in. The center is 0. We're at the fifth derivative, so n equals 5. So we're going to put 6 in here, and function has a fifth derivative. Okay, hold on. Taylor series, degree 4. So n equals 4 for the function, so n+1 would be the fifth, which makes sense with us using that derivative. So on my calculator, if I'm doing this on my calculator, I'm going to do 72 times 0.5 to the fifth divided by 5 math PRB number 4 factorial, and we get 0.01875. So that's your Lagrange error bound. Don't truncate if you're gonna cut off something. Actually, just round. You got to round up. So I don't know. Didn't say how many decibels to give. All right, next one. This is your function. Taylor polynomial, degree 5, n equals 5. Centered at x equals 0. Approximate 0.2. What's the Lagrange error bound going to be? So I think we need to get to the sixth derivative. So I'm going to take these. This is the little bit of the tedious part. The 0th derivative is the original function. The first derivative is 3 cosine 3x. The second derivative is -9 sine 3x. The third derivative is -27 cosine 3x. The fourth derivative is +81 sine 3x. The fifth derivative is 243 cosine 3x. And finally, the sixth derivative is -729 sine 3x. All right, so that's what we got to use. Okay, so Lagrange error bound. See if you can write it from memory. It's like the next term in a Taylor series. It's the n+1 derivative at some value c. That's the only difference is the c thing. X minus a is the n+1 power over n+1 factorial. So for us, we're specifically looking at the sixth derivative at some value c. The x minus a to the sixth power over 6 factorial. So numbers wise, I'm gonna I'm just graph this sine curve. Looks like this. Period is 2 pi divided by 3, which is about 2, right? Pi is about 3. It's a little more than 2. It's about 2. So this is about 1. Little more than 1. And we're looking at 0 to 0.2. Now we're evaluating sine point. We were trying to estimate sine of 0.2. So be careful. That doesn't mean, that's not what x is. X is the value of x that would make 3x give you 0.2. So x is 2/30ths, 1/15th. That's your value of x. So we're looking for a c value between the center and the x value 1/15th. Now 1/15th is pretty small. I mean, what is that? 6. It's like, I don't know. It's less than 0.1, right? 1/10 would be 0.1. This is about at 0.5, right? So 0.1 is going to be somewhere over here. So what's the biggest value? Well, I can identify it's right there. Whatever sine of 0.2 is, or not sine, 729 sine 0.2 is going to be the biggest value right there. So we're going to put 729 sine of 0.2. So some of you guys, after the few examples I showed you, might just say, I'm always going to put the amplitude. Okay, but that's worse than worst. The amplitude is way bigger than this worst value right here. This is worst case scenario right here for the interval of values you're supposed to consider. So the x value is 1/15th. The center is 0. 6 power over 6 factorial. So I'm going to put this in my calculator. So I'm going to do 729 sine of 0.2, parentheses, 1/15 raised to the 6th power divided by 6, math, PRB, number 4 factorial. And I get 1.76549 times 10 to the negative 8th. So let's say we're doing 3 significant figures, then we would do 1.77 times 10 to the negative 8th. Definitely going to round up. Don't round down. Okay? Now, my answer that I showed you guys was wrong at the beginning. It should be 1 point. Oh, no, I'm sorry, it's right. Let's cross out the wrong one. Okay, just double checking. Okay, so, all right. Next one, approximation for e to the x. There's a series used when x is small. Find the Lagrange error bound when x is 0.2. Okay, so we need that next term right there, the derivative that does that. So the original 0th derivative is e to the x, original function. F prime is e to the x. Oh, this is easy this time, right? Just e to the x, e to the x, and we want the 4th derivative. Because for our Lagrange error bound, which is generally the n+1 derivative at a c value, x minus a to the n+1 power over n+1 factorial. For us, it's going to be the 4th derivative at a c value. X is 0.2. This is a Maclaurin series, so it centers at 0 to the 4th power over 4 factorial. And so this is the series right here. I'm going to just draw a quick sketch. It's an exponential function. We're looking at 0 to 0.2, this chunk of the graph, right? So what's the biggest value? Well, right here, when you plug 0.2 into it. So the biggest value is e to the 0.2. and 0.2 to the fourth over 4 factorial. Or if you don't like that, draw on that graph, do full-blown stream value theorem. Those are your endpoints, find your critical points, make a table, justify it all like that if you really want. Okay, e to the 0.2 times 0.2 to the fourth divided by 4 factorial is 24. I can do that in my head quicker than typing it in. It's 8.142685 times 10 to the negative fifth. So we're going to go with 8.15 times 10 to the negative fifth. We're always going to round up. No rounding down, no truncating for error. Okay, so I guess on my solutions, I may have written that one down wrong. It should be 8.15. All right. Okay, number 9. How many terms in the Maclaurin series for f of x are needed to compute the natural log of 1.2 within an error of at most? So we want the error to be less than or equal to that. So this is kind of like, I think, number 5, where we tried a bunch of different n values until we got one that satisfied it. So if you, by the way, if you're, I don't know if you just want to remember what this series looks like. It came from integrating 1 over 1 plus x, right? And that series is 1 minus x because r is negative x, plus x squared minus x cubed, and so forth. And so then the series equals natural log of 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. Okay, so that's the series we're dealing with. Anyways, when n equals 0, that's usually the first term. So n equals 0. It says how many terms, though. N equals 0 would be 1 term. Okay? And you would rely on the 0th derivative. Is natural log of 1 plus x. Now remember, Lagrange error bound is the next derivative, n plus 1th derivative at a c value, x minus a to the n plus 1 power over n plus 1 factorial. For us, the center is, or the x value is not 1.2, 0.2 minus the a value is 0. Right? Not 1.2, because look, it already has a 1 there. So if we're estimating natural log of 1.2, that means we're plugging in x equals 0.2. All right, so we would need the next derivative, 1 over 1 plus x, to plug that into here. So when n equals 0, and we have 1 term, you're going to have to use that derivative. L.E.B equals, well, we got to look at this function and say, what's this is a rational function, right? I'm gonna draw a little picture over here, and it has a vertical asymptote at x equals -1. And when you plug in 0, it's positive, and you plug in -2, it's negative, and it has a horizontal asymptote. So we're looking at 0 to 0.2, this chunk of the graph. So the worst value is when you plug 0 in, and it's 1. So you get 1 times 0.2 to the first power over 1 factorial. So it's going to be 0.2. Is that less than 0.0001? Nope. Okay. Okay, so now we're going to go with n equals 1, which would be the same thing as 2 terms. And we got to find the next derivative, the second derivative. The second derivative is, I would think of this as 1 plus x to the negative 1. So it's going to be 1 over 1 plus x squared. Now that function is also a rational function with a vertical asymptote at negative 1. But because of the squared on the bottom, it's top or bottom. The negative on the top means it's down. So that's what that graph looks like. And 0 to 0.2, the worst value is, again, when you plug in 0. I mean, you could try if you plug in 0.2, you actually get a smaller answer. So if you plug in 0, you get negative 1. Negative 1, 0.2 squared over 2 factorial. So on my calculator, 0.2 squared divided by 2, and you want to do the absolute value. So you get 0.02. Is that less than 0.0001? Nope. Okay. If you feel like you're way off, you could skip one of them in between, and hopefully you don't overshoot it. But we need for n equals 2, 3 terms, we need the third derivative, which is going to be positive 2 over 1 plus x cubed. So this graph is going to kind of look like the last one. It's going to have vertical asymptote x equals negative 1. Actually, when you plug in negative 2, ends up being negative. So it kind of looks like that one a couple ago. So 0 to 0.2, again, 0 is your worst value. So you plug 0 in here, you get 2, 0.2 to the third power over 3 factorial. So yeah, it's a little tedious. 0.2 to the third power times 2 divided by 6. 0.00266. Is that less than 0.0001? Nope. All right, I'll keep going. N equals 3, which is the same thing as 4 terms. Okay, so we need the fourth derivative because we're doing n equals 3 third order or third degree. So this is going to be negative 6 over 1 plus x to the fourth. So this one actually looks a lot like the second graph I drew. Vertical asymptote, both on the bottom. So I'm going to go with just that rough sketch and say, okay, plugging 0 into the worst case, which is negative 6, 0.2 to the fourth, over 4 factorial. Plug that in my calculator, 0.2 to the fourth times 6 divided by 24. It's 4 times 10 to the negative fourth, which means we're going to move the decimal point over 4 spots. So it's going to be 0.0004. Is that less than 0.0001? Almost getting close. It's a little bigger still. So I'm thinking the next one should hopefully be right. Okay. So we got to just do one more derivative. This one's going to be positive 24 over 1 plus x to the fifth. So this is going to look like the original graph or the last graph I drew. And so I'm going to say, oh yeah, plugging 0 in is going to give me the worst, which is going to be 24, 0.2 to the fifth over 5 factorial. And I'm hoping this is it. 0.2 to the fifth times 24 divided by 5, math, PRB number 4 factorial. And we get 6.4 times 10 to the negative fifth, which is, we're going to move the decimal place 5 spots, so 0.00004064. Is that less than 0.001? Yes, finally. So the n value is 4, the number of terms is 5. But that's how you do it. You guys, have a couple problems like this on your next test, and you just gotta kind of work your way through it and support your answers. Got little pictures to find your C values. Okay, next one is closed form, open form, Maclaurin series for fx. Find the value of the 12th derivative of f of x. The 12th derivative of f of x. Well, I'm going to try and use what they've given me. This should be the 0th derivative over 0 factorial. This should be the first derivative over 1 factorial. This should be the second derivative over 2 factorial. This should be the third derivative over 3 factorial. So, I don't, okay, let's see. At the 12th derivative. Okay, here's the deal. So, I'm going to use this pattern and I keep writing. I want the x to the 13th power term. Okay, so the next term is going to be x to the 5th over the pattern here. It would be 4 factorial. 6 over 5 factorial. In fact, I think I'm going to jump to the x to the 13th term over 12 factorial. And the coefficient, which is right here, and including that, okay, so the this coefficient, this would be f to the, okay, hold on, 12th derivative. So the 12th derivative, and times x to the 13th over 13 factorial. Does that make sense? You know what? When I started this, I might have been messed up. My f of 0 might have been 0. I mean, the derivative should match up to the power. So the pattern is, I'm going to put a 12 here, and then I want 11 factorial in the bottom. The pattern here is the factorial in the bottom is always one less, okay? So that means, okay. Let me rewind one more time. If we want the 12th derivative, okay, let me start over. If you want the 12th derivative at x equals 0, the center, then you need x minus a to the 12th power over 12 factorial. That's the term that's going to have it. Now, from this pattern, I know that this term is going to look like this. It's going to be x to the 12th, but it's going to be over 11 factorial. So I need to set the 12th derivative at 0 over 12 factorial equal to 1 over 11 factorial. And now I'm going to solve for the derivative. And I get the 12th derivative at 0 must equal 12. If I simplify that, must equal 12. All right. Sorry, that took me a little while to come back to. That's it. So